Okay, so good afternoon, everybody. My name is Alexander. I'm here with Diogo. We are software engineers from Nubank, and today we are here to talk a little bit about what some of scaling challenges that we have, how we can support over 5 million customers today, and how we plan on keep on growing. So we're going to talk a little bit about some AWS products that we use, some strategies, some open source software as well, and then we can discuss about how some of this that we are going to talk about may apply to your company and how you can use, I hope you can use some of this to make your lives better. So to begin, a little bit about Nubank. We are a company all the way back from Brazil. We've been around for 5 years, and we are a digital branchless bank. All the way back from Brazil, and we started with a credit card. It was our first product, was like a no-fees international credit card with no hassles, no anything like this, very easy to use, everything done through an app. We also then got our rewards program, everything working great for the customer. And the third product was our own version of our bank account. And we've been doing this for 5 years, and we are proud to say that we are the largest digital bank in the world outside of Asia, with over 5 million customers on our credit card. And to get here, we have to go through a lot of things. And we do what we call cloud-native banking. So we were born in the cloud. We never did like a cloud transition because we've been using the cloud since the beginning. And it gives us a lot of things. One of those things is autonomy. So our teams, they are empowered. They can execute independently. And they don't have to sync everything that they do with each other, which helps us a lot on velocity, which is the second thing that we have by using the cloud. So we can evolve fast, we can do very small increments and just grow and grow and grow, which is very nice for us. It was also strategic for us because we had a very low upfront cost, so we could grow as we scaled. And on the security side, it was also very important because, well, the financials industry is built upon trust, and if no one knows who you are, they don't trust you. So by leveraging the cloud, we could make use of a lot of security features to make our product trustworthy and for the customers to see that we were a serious company that they could do business with us. And we have been growing quite a lot. We had almost like 2 million people that applied for a credit card. We gave it to 5 million of those people. And it has been used in like almost 200 countries, which is quite nice in over 5 years. And on the technology side of things, we have a little over like 500 million daily HTTP requests, 200 million Kafka messages daily as well. We do more than 50 deploys a day, and that happens pretty much every day. We have more microservices than people, so on the engineering side. So we have like a little over 150 engineers and over 190 microservices. But not everything is great, so we faced some challenges to get where we are, and we faced some scalability bottlenecks. The two main scalability bottlenecks that we faced were writing to our databases, and then we're going to talk a little bit more about that later, and also how the lag between the messaging in between our services were impacting the customer experience. So we had to come up with a plan that would make us be able to scale and solve those issues. So the idea is, well, we wanted to split the workload. We wanted to be able to make our workload separate. But the thing is, on our business, there is not a very high level of interaction in between customers. So, I mean, like, they can do like transfers between each other, but that's not a thing that happens all the time. So it is safe for us to have our customers separated into some kind of logical units. So that's what we were aiming for. So we came up with 2 plans, and then we tried to see what would be the best idea. The first option that we had was splitting databases. So we were already using microservices, or services were not sharing databases. That was great. So we could just like shard those databases, and that will solve the database write throughput problem that I was telling you about. And then we would just change like the code on the server on the service to route the query to the correct database, depending on the customer that you was referring to. But there were a few issues with that model. First, we would have to make change to our production code in all of our services. It also only solves the first problem that I talked about, which was a database writing problem. And there was a right risk of mixing the business logic with the infrastructural database code, so we were not sure how that would play out. Because at the end of the day, there was a high risk of introducing new bugs to our code. So we thought of a second option, which was, instead of sharding the databases, why not shard the whole infrastructure? So we came up with the scalability units that we call them shards, which is basically separate copies of Nubank. They are not aware of each other. And in each of those copies, lives a subset of a customer. So a customer lives in a single shard. Everything related to the customer lives in the same shard as well. And then we can basically scale horizontally as much as we want, because we can just spin a new shard whenever that's needed. But we couldn't just have like 1, 2, 3, 10 separate copies of Nubank and call it a day, because that would not be enough. We also needed some kind of routing layer. So we built what we call the global routing layer, or the global shard, which is basically, let's say someone from another bank wants to make you a bank transfer, like a wire transfer. The other banks, they have no idea what shard our customers are, because that's not something that is part of the banking and financial mechanics. So we have this layer of services. They are microservices, and same as the shards, that whenever we get requests from the outside world, they go only to the global routing layer, and what they do over there is route the request to the correct service on the correct shard. So in this case, like a transaction comes in, it looks up, okay, so this is for this customer is on shard 4, so I'm going to route this request to the service responsible for taking in transactions that is running on shard 4. So that is what we did when we wanted to make it easier for us to scale. So in each shard, we have the all the services, all the databases, all the Kafka brokers, all the zookeepers, anything that we need to make the shard run is within the shard, and they are not aware of each other. That makes it easier to scale, because, well, we have this global routing layer. We have the first shard, which is like shard 0, which is the shard before shards existed. And then, okay, so let's spin up a new shard, and let's start putting like all the new customers in that new shard. And then it had less resources than the first one, because it didn't need to. And then it could just scale over time, and you will get a very easy way to scale. And then when that was like hitting any kind of bottlenecks that we didn't want to scale vertically anymore, we could just spin up a new shard. And then we kept doing that, so we could like have basically an infinite, potentially, numbers of shards. And a nice thing about that, like a little nice side benefit, is that it also reduces our blast radius, because it's very hard for something to impact the Nubank's infrastructure as a whole. It's easier, like for when something wrong happens, to impact a single shard. So that would impact only the customers that live inside that shard. It would not impact the whole of Nubank's client base, basically. And to make these things happen, we have a lot of stuff under the hood. So I'm going to hand it to Diogo, that is going to tell you a little bit more about that.
So hello. So sharding architecture is helping us a lot, and there is a lot of benefits, but none of this comes out of the box. So I'm going to show you some technologies and practices we've adopted to make it possible. And the first one is Clojure. Most of our microservices are written using Clojure as a main language. For those who don't know, Clojure is a Lisp language that runs on JVM. It is functional, immutable, it enforces immutability. It's a small language, so it's simple and easy to learn. We can have quick feedback, developing and test things using REPL workflow, and it's gradual typing. Gradual typing is like we can develop our system using dynamic types, but use schemas to ensure some data structures when necessary. For database, we use Datomic. And Datomic is a database with immutable characteristics. It's like a Git for data. There is no update in place. That means you never lose data. And it's pretty important for a financial system to never lose data. So in a normal SQL database, if you have a credit limit column in a customer table and you do an update, you lose that data by default. You don't have the historical data. In Datomic, an update is just append the new data, keeping the old one for consulting. So with this superpower, it's easy for us to make queries in the past and check, for example, his or her limit, how many times the customer limit has increased last year. Another interest characteristic on the Atomic is that it runs over the storage layer. So we can have different storage for many things. In your case, for example, we use different storage for each environment. So during development, we want to be fast. So we use in-memory database for it. And in production, we use DynamoDB because we want to scale as much as possible. Another core technology in our system is Kafka. Almost all our interactions between our microservices is done through Kafka messages. And we choose Kafka because, different from other message systems, when a system processes a message, this message keeps persisted there. It doesn't disappear. And a funny story, once we had services up and running in production using an in-memory database because of a misconfiguration, and it could be a completely disaster. But how Kafka keep the message persisted, we can reprocess the message as many times as we want. So we just fixed the configuration, reprocessed the Kafka messages, and got completely recovered by that. So this persistent characteristic of Kafka brings for our architecture a lot of resilience out of the box. And we also implemented some other resilience patterns. For example, dead letters for message that fails during the process. Integrated circuit breakers. So for example, if the database component is start to failing, the circuit breaker of Kafka will start to make back pressure and reduce the amount of messages being consumed so we don't make the things worse. The new core technology in your infrastructure is Kubernetes. We're going to talk more about it later, so I'll keep for. And of course, AWS. We are running on AWS since the beginning. We are heavy users of CloudFormation, heavy users of DynamoDB. We have an interest case in using Lambdas for security. AWS has been amazing for us since the beginning. So, since this charging architecture consisting make many copies of our infrastructure, we had to invest a lot of effort in your automation. And to do automation, we needed to have infrastructure as code. And in Nubank, we treat infrastructure as a software engineer problem, and we separate it in two core projects. The first one, definition, is the project where contain all our deployable units defined there. And we use EDN for that. EDN is like a JSON for closure, but with superpowers. And why we use that? What is the benefit on using EDN? Well, almost all our engineers are used to work with closure. So if we use something for infrastructure that are similar with the software, they get comfortable and confident to make changes and taking care of their own services infrastructure. So it helps in the ownership. The other project is deploy. Deploy is where we write down our automation and our recipes. It's kind of the project that reads the definition and interact with AWS API to create the resource. So this is the definition repository. As you can see here, everything on our infrastructure must be here. It's kind of a source of truth of our infrastructure. And we have not only technical components, but some organizational structure as well. For example, squads. And that's here because we want that every component on our infrastructure belongs to a squad. So with this way, we can halting alerts in an easy way. So for example, this component belongs to this squad. So if something is failed, we are alerting this squad about his components fail. Mm-hmm. So here is how a EDN looks like. This is a small sample of our environment definition. So here we can define how many shards there is in each shard. So if you take a look at staging, for example, there is just 2 shards plus global. And that's because we don't need to have a huge infrastructure on stage. We just have to ensure that the sharding architecture is working well. And so we follow the assumption that if it's working for 2, it will work for n shards. And in production, otherwise, we have 7 shards plus global right now, but we can increase as long as we are growing. So there is other interesting things here that we can do. For example, define some default specs for our services. So in a stage, for example, we don't want to spend a lot of money. So the default instance type of our workloads is like a burst small. That is an abstraction of us that is equivalent to a T2 small AWS instance. And in production, otherwise, we use a higher workload with a mean size of 2 for high availability purpose. And we can add other things like JVM flags and whatever we want here. So once we have our environment defined, the squads can define their service specs in a similar way. So I brought you here samples from billing. That is the service that deals with billing process, and auth, that is the service that deals with authentication and authorization. So if you take a look here, we can define where the service is going to run. So billing, for example, runs inside the shards, while auth runs inside the global route layer. And we can also override those environments defaults. So for example, billing needs at least 8 instances running to work in a healthy way. And auth, for example, needs a higher workload and other scaling policies. So this is a simplified flow of how deploy and definition interacts to create our infrastructure. So basically, definition uploads everything to S3, and deploy reads the definition bucket, translates it to CloudFormation, and CloudFormation creates all AWS resources for us, and then deploy interact with those AWS resources to create the services and deploy the stuff. So, but how we evolve our infrastructure? Well, if you take a look at the technologies that I've mentioned before, all of them has immutability in some way, enforce immutability in some way. And with this functional mindset, we made the same on our infrastructure. So I'm gonna show you a little bit how we do immutable infrastructure in Nubank. So first, what is immutability, right? A lot of people talking about having immutable infrastructure, but what is immutability? Well, I like to say that immutability is like taking a step forward with the possibility to take a step back if necessary, if something goes wrong. So we can imagine, like for example, a Save Yes button on a Photoshop. So you have a 4K photo, and you want a small version of this photo. So if you just open the Photoshop, resize the image, and save in the same file, you have mutated that photo. So you lost the original one. But if you use the Save As button, you are creating a copy of this photo with the change that you want. So it's easier to, you can always return to the original state. So you never lost your original state. But why we choose it and how it's applied on our infrastructure. So imagine that you have a zero-day vulnerability, like a meltdown case. Or you have to upgrade your operational system that runs your Docker containers. Or you have just to change a system unit D that forwards the log for your log provider. Well, you can just SSH into the instance, make the change that you want, and everything is going to be fine. But you have mutated the state of that instance. So you can recover for a last version. And it's not good because imagine that you are working in a large scale. So you have thousands of instances, and you have, for example, multiple AWS accounts. So if you think, for example, like, well, I'm trying to SSH into all instances and do it. And even that you have a tool that does it for you, or a script that does it for you, you will end up with an inconsistent state, and you are trying to debug something that's not easy, and that's a sad engineer trying to fix something working until late. So, well, so how we do in Nubank when we want to do those changes that impact a lot of instances? Well, imagine this scenario. We have a version 1 of Nubank production environment working. So we make the change on definition to reflect the change that we want. And we use deploy in the same workflow that I showed you before to create a new version of this infrastructure. And the important thing here is that it's not like a deploys. The whole infrastructure is like all services, all VPN, all VPCs. It's like everything is going to create a new version here. And so if everything is fine, we have some monitoring and things that let us know if everything is running well. So if everything is well, we start to forward the traffic for the new version. And if something goes wrong, we can take a step back and just get back to the older version. But in a help path, we stop to forward the traffic for the old version, and then when we feel comfortable, we can kill the older version, and that's it. So what is the benefit on it? Well, we can have short feedback loops. So we can test our automation process. We can test everything related to our infrastructure creation in an easy way. We can quickly recover from incidents during this period of changes. And we created like a fearless culture in Nubank where engineers are comfortable to taking risk doing those big changes because we can recover quickly from it.
So we talked a little bit about some of the components of our infrastructure. And as you can see, we're heavily based on immutability. So our programming language focus on immutability, our database focus on immutability, our messaging system focus on immutability, and our infrastructure is based on immutable concepts as well. So I'm going to give you now a practical example of how this immutability-based focus helped us move to Kubernetes with very little issues. So just a quick recap for those who don't know it, Kubernetes is a container orchestration platform. Is very good for a microservice architecture, which we were already using. It also enforces immutability on the infrastructure as well, so this aligns with what we like to do. It makes it easier for us to interact. It has lots of self-healing capabilities and dynamic auto-scaling. So looks like a good fit for us because we already had those things with our previous environment, but in Kubernetes, it was just all of those things we will get them faster. So what happened was we wanted to migrate to Kubernetes, but we didn't have to have any downtime or any problems for our customers and for our development team as well. So going back, this is how our deployment process worked. We had everything, services, databases, everything defined on the definition repo. Then that would go to S3. The deploy project would read everything, generate crawlout formation templates, and that will create AWS resources like EC2 instances, IAM roles, security groups, load balancers, everything that was needed to create. So what we did is, since we have this automation layer in between the developer and the actual production system, we just changed on the deploy side of stuff. So now, instead of creating EC2 instances to put each service in a single EC2 It still creates CloudFormation templates, but it creates the templates to generate the Kubernetes cluster. And then it deploys those Kubernetes clusters to AWS and uses the Kubernetes API to create the containers for the applications inside the Kubernetes cluster. So from the point of view of our developers, there were no major changes. Their process was still working on the same way. But on the infrastructural side of things, those are very, very different environments. The EC2 only based environment and the Kubernetes environment, they are very, very different. But we did this migration in a way that was very, very seamless for everyone involved. And as everything that we do blue-green deployments for our services, we do blue-green deployments for our infrastructure. So we did the same things for the shards as well. So we had one shard that was running already based on those CloudFormation templates that generate the EC2 instances. Then we just created a Kubernetes cluster, and it started to forward traffic to it. So a Kubernetes cluster with all the same services. It was working fine, so we just deleted the whole infrastructure. We tried that in staging. We checked it was working fine, so we did it in production. We got some little issues, and then we just fixed them, and then we wrote back, fixed it, did it again, it worked. We got comfortable with the process, and then we just did it for all the other shards as well. So by the end of the day, we deleted all of our old infrastructure and replaced it with Kubernetes. And we were able to do that because we were based on immutable concepts from the ground up. Like we really like that because it gives us a lot of flexibility. But it needs a lot of work on the automation side to make it work, of course. So what can we take from this? Well, first thing is on the scalability side of things. The cloud is very elastic, that's true, but it's only elastic as your architecture allows it to be. So if your services, if your infrastructure is not built for elasticity, there is no point in just spinning more EC2 instances because that's not going to get you anywhere. You have to think how your services interact. You have to think how your infrastructure interacts, how you create it, how you update it, how you migrate it to make it use of that scalability capabilities of the cloud. Second one is velocity. We are just as fast as our automations. So when we had just one shard, we could do some manual updates, but now we have 7, we might have 10, we might have 20, so that just doesn't scale. People alone, they don't scale. We need automation as well. So the cloud is very fast. It can give you resources as long as you want, but if you're not built to use those resources, you're not going to be able to enjoy the velocity. Also resilience. You have to plan for whatever failures that might have. And being immutable helps a lot because you know there is always a safe state to go back. So whenever you are trying to do any kind of changes, it might be on the database side, on the service side, on infrastructure, it doesn't matter. If you focus on never updating things in place, always doing things in an immutable way, you can always go back, and it helps to troubleshoot things a lot. So you don't want to be waking up 3 a.m. in the morning and have to debug something. You just want to, okay, I can roll this back, I can take a nap, and I can go back to work tomorrow and actually fix the issue. And also autonomy. So having our infrastructure defined as code makes anyone able to deploy it. You don't need a very specific kind of people doing that. You don't have a team that just deploys things. Everyone is able to deploy. Everyone is able to ship things to production. We don't have a team that is only looking at infrastructure alone. Like we have people that try to automate our infrastructure, but at the end of the day, the responsibility for each service's state is from each of the squads, not of a single team. So these are some of the things that we learned from here today. If anyone is interested in those things or like to talk to us, we are hiring. So you can go to this link or talk to us after all. And we hope that the things that we were talking here about today are things that may help you do this on your organizations. And again, we're not saying, okay, you have to use Clojure or Datomic or Kafka or Kubernetes. It's not the tools that we use that really matter, but it's the concepts that matter. If you focus on being able to do things safely and being able to roll back things, you can get a lot of velocity, a lot of autonomy. So with that, we finish, and thank you so much.